Okay, logic class Friday afternoon. Class just ended. We gotta push on. We're going too slow. We gotta be fast. So we're gonna make a video right now. I mentioned a week ago or something that I would make a video about propositional logic. We did some in class today. Let's do more now. All right. So at the very end of class, I threw some definitions in front of you. And what counts as a tautology. A tautology is something which is always true. I claimed that P arrow P is a tautology. Well, the proof of this is quite simple because P is just one propositional variable. Therefore, the entire truth table for P requires me to only consider two possibilities, that P be true or false. So how do I do P arrow P? Well, okay, if it makes you feel better or something, you can like rewrite it, but that's really not necessary. What is P arrow P? Well, I just use the definition for arrow. The definition for arrow says that P arrow, let's just do it. True arrow true is true, and false arrow false, according to what we talked about in class, is also true, and therefore this is indeed always true. This is what's called a tautology. It's always true regardless of the truth value of these propositions. And then there are things which are always false. An example of something which is always false is P and not P. Okay, if you've never somehow done this before, here it is. You take your proposition P, it's either true or false, and then you say, okay, well then not P is false and true. Oh, by the way, I did not give the definition of not in class. Well, here it is. It is a connective. Not is called a unary connective. A unary connective, as opposed to a binary connective. A binary connective connects two propositions. A unary connective connects just one proposition. So P and not P is just so not P, this is the truth table for not P, this is the definition of not. It's more or less how not works. It just reverses the truth value of the underlying proposition. Okay, and so if I want to make the truth table for P and not P, I just build it up one step at a time. If you and together a true and a false, it's false, and if you and together a false and a true, it's also false. So indeed, we see that the sentence P and not P is always false. And so this is called, I call this an unsatisfiable, this is an unsatisfiable proposition. It is impossible to come up with a truth assignment in which it is true. Okay, and there are some other connectives out there. There's a couple more that maybe you've heard of. There's exclusive or. So how does exclusive or work? Well, you just kind of know this from theoretical computer science. So true, true, false, false. 1 second. Yeah. So if you say P exclusive or Q, then you want that to be true when one or the other of them is true, but not both. And so you want it to be true when P is true or Q is true. False when they're both false, but also false when they're both true. So you can have soup or salad. If that is written on a menu, then typically that is interpreted as you are being told that you have to choose one or the other. If the buffet says you can have soup or salad, but you go up to the buffet and you take soup and salad, then you've just performed some kind of violation. So your promise would be false. Okay, everyone's seen that before? There's another one that you have seen before, but you might forget, and that is nor. Nor is its own connective, and let's talk about nor for a minute. What is P nor Q? Well, it's basically like it's supposed to capture the English. It's supposed to capture the English use of the phrase, nor. So if the sign, you're at some weird buffet, and the sign says you may have neither soup nor salad, then what they're telling you is you can't have either of them. So if you should suddenly take both soup and salad, well, you've certainly violated the rule that says you may have neither soup nor salad. But if you just take soup and not salad, you've still violated the rule. Salad but not soup, you've violated the rule. The only way to make it true is if you just take nothing. So that buffet, basically, to satisfy that buffet commandment, you have to just not take either of the things. So okay, there it is. That's the truth table for nor. And so okay, maybe I'll just leave that there. There's one more or something, but well, I guess I have to kind of include it somehow. Man, I need a bigger board. I guess I'll just go this way, even though that's kind of awkward. There's this symbol, this sort of double arrow thing. What's up with this double arrow? Well, once again, I can just mindlessly tell you, and you have to sort of accept because it's a definition, what P if and what this double arrow is, and the answer is it's true when the two atomic propositions have the same truth value. So it's true, false, false, true. And people often pronounce this P if and only if. Q. That is a very common English phrase. And alright, I'm not sure whether it's worth doing this. I didn't do it in class. It's in the packet. But you can kind of walk through, if you would like, a slow examination of this sort of very artificial phrase that mathematicians try to use a lot, if you want to kind of understand what it means. And I guess it goes something like this. Okay, let's make up an example. So I don't know. I will suppose this is your sentence. You say I will. One second. I'm trying to think of something funny but boring. I will go to the zoo. Go to the zoo only if you pay me. Okay. So great. I will go to the zoo only if you pay me. Okay, this is just coming up with a completely arbitrary sentence which uses the phrase only if. And so what we are now doing is a kind of a sort of lazy linguistics in which instead of doing actual research about the way people use only if, we are native speakers, and so we're just sort of creating artificial sentences, and then we're just going into some sort of deep think and trying to figure out what they mean, and then we're pretending that that's sort of holds universally for all people who use this word, and it mostly works. Here is the first proposition is P. I will go to the zoo. And the other one here is you pay me is Q. Okay, so let's try to figure out what this sentence means by examining all the possibilities and then learning. So okay, we do it. Man, I guess I'm just doing this all over again. Okay, so PQ, and here is P only if Q. Okay, well, what happens if you make this promise and then, yeah. Okay, let's get a name in here. So Jared. Just generic name. Jared will go to the zoo only if you pay him. Okay, I was running into some pronoun issues there. Okay, so what if Jared does go to the zoo and you pay him? Well, it seems then that the sentence is true, because hold on, one more time. Should just stick with my old examples. I say, I will go to the zoo only if Jared pays me. Okay, here we go. So now I can use sort of you and I interchangeably. So someone utters this sentence: I will go to the zoo only if Jared pays me. Okay, and now what if you go to the zoo and Jared does pay you? Then it seems you've kept your promise. Or rather, you should perhaps think of it as going in the other order, right? Jared pays you, and you go to the zoo, and so it seems like you've kept your promise. We're going back to the promise way of thinking about conditionals. Okay, what if you don't go to the zoo, but Jared does pay you? Well, that's a little bit disturbing. Jared pays you, and yet you don't go to the zoo. But you promised you would go to the zoo only if Jared pays me. This example is not really working for me so well. I'll go to the zoo only if Jared pays me. Okay. I think you have now broken your promise. Because you have said, I will go to the zoo only if Jared pays me, and yet Jared didn't pay you, and you went to the zoo anyway. You broke your promise. You said you'd go to the zoo only if Jared pays you, but he didn't pay you, and yet you still went to the zoo. False. Okay, continuing on, what if you just don't go to the zoo, but Jared does pay you? I think I'm doing this right. Alright, well, what if, let's examine that, right? So you don't go to the zoo, but Jared does pay you. Have you kept your promise? I say yes. You actually have kept your promise because, and maybe this isn't the best example, but I will go to the zoo only if Jared pays me. But you're not saying that you necessarily will go to the... This example sucks. Maybe I should just go back to the example that I've been using for 10 years. It works so perfectly. It's actually the very example that's on your packet, so we might as well just use that because it's sitting right there on your packet. I will marry someone. I will marry someone only if they're rich. Okay. So this is a position that you might take. You're only going to marry a rich person. So I will marry someone only if they're rich. Okay, here's P. This is Q. Maybe I should just look at my own notes. Since I made a whole page of this, and I posted a link to it. So I should use it. Okay. So I'll marry someone only if they're rich. Okay. Going through this a little bit faster now. What if you do marry someone and they are rich? Okay, you've kept your promise. If you marry someone but they're not rich, I claim you have broken your promise because you said I'll marry someone only if they're rich. But here you just married someone who's not rich. You said you'd marry someone only if they're rich. This person's not rich, and yet you married them anyway. You've broken your promise. You promised to marry someone only if they're rich. I feel like that one flows a little bit better than this stupid kind of Jared Zoo thing. Okay, what if, on the other hand, you don't marry someone, yet they are rich? In other words, you meet a rich person, but you don't marry them. Well, that seems like we're still okay now, right? Because you said I'll marry someone only if they're rich, but you didn't, perhaps you just never met a rich... No, you said you'll marry someone only if they're rich, but that doesn't mean that you say that you will marry someone just because they're rich. It doesn't mean that, this doesn't say that you're going to marry the first rich person that you see. If you meet someone who's rich and you don't marry them, you have not broken this promise. Your promise was to marry someone only if they're rich. You're not saying that if they're rich, you'll marry them. I think that's an important distinction. If you say this sentence over and over again to yourself several times, I think it's pretty clear. And then, this video sucks. All right, keep on going. What if they're both false? What if you meet someone who's not rich and you don't marry them? Then I claim that you have also not broken the promise, and hence we should interpret the sentence as being true, because you said you'll marry someone only if they're rich, but if you just don't marry some non-rich person, then you've still kept your promise. Okay, so that was a bad explanation, and it took way too long. It was kind of not even really fun. But I hope I have convinced you via this process of saying this sentence over and over and over again and sort of examining what you know deep down it means, that this is actually the correct truth table for the English connective only if. That's the whole point of what we're doing right now. We are examining in isolation, or attempting to, this expression only if, and we're trying to figure out what it means. And I claim that this is what it means. And actually that's just quite interesting, because this is precisely the truth table for P arrow Q. We know that that is true, true, false, true, true. And so I feel like I've discovered somehow, by analysis, by linguistic analysis, that the only if connective just means the same thing as the arrow connective. That's kind of weird. Alright, what if I change this now to I'll marry someone if they're rich? Okay, one word difference, and now suddenly the meaning of the sentence has completely changed. So let's examine it. P if Q, P if Q. Now you're saying, I'll marry someone if they're rich. Well, now if you marry someone and they are rich, it seems you've kept your promise. If you marry someone and they're not rich, I claim you have still kept your promise. Because you're basically saying, I'll marry someone if they're rich. But, which is maybe could be interpreted as saying you're going to marry the first rich person that you meet. You're going to marry them if you have the possibility, or at least you're willing to if you have the possibility. But what if you just never meet a rich person in your entire life, say, and you just marry someone that's not rich? You haven't broken your promise. You didn't say you wouldn't. Okay, let's keep going. What if you just don't marry someone even though they are rich? Well, now I claim that really your promise has in fact been broken, and this new sentence should be false. Because you said you'd marry someone if they're rich, but this person is rich and yet you didn't marry them. Okay, and if you simply don't marry a non-rich person, then you've also kept your promise. You said you'd marry someone if they're rich, but if the person's not rich, then you're free to do whatever you want. Okay, so upon a close examination of P if Q, I have determined that this is the truth table for P if Q. Okay, big surprise. This is, okay, if you're sort of recognizing this pattern, this is in fact just the pattern for Q arrow P. And so, okay, this is kind of anticlimactic. The correct interpretation of P if Q is just if Q P. Okay, in other words, this sort of phrase of English, P if Q, is just a different grammatical way of saying if Q then P. Just because it comes second, the antecedent of the conditional, the if part, is still the Q. So in other words, saying P if Q is just a different sort of poetic flourish of saying if Q then P. Okay, therefore, and because this, because Q arrow P, I should say, is true arrow true, true, false arrow true, that's still true. True arrow false is the only way to make the Q arrow P conditional false, and false arrow false is true, assuming the conditional is true. Okay, this is an entire, basically wasted 10 minutes. What have I done here? I have convinced you of the interpretation of this only if and this if thing. And, this phrase of English, if and only if, this very artificial thing that no one would ever say except a mathematician or someone who's been hanging out with mathematicians, P only if and only if Q, is just shorthand for P if Q and P only if Q. In other words, this is a sort of fast and compact way of saying P arrow Q and Q arrow P. And if you produce the truth table for P arrow Q and Q arrow P, these are the sort of the constituents of this sentence P if and only if Q, well what you get is this is true, false, true, true. This is, as we just said, true, true, false, true. And when you AND these two together, you get precisely this right here. Okay, that is why, everybody pronounces this symbol if and only if. And I hardly think people are even really thinking when they're using P if and only if sentences anymore. P if and only if is really just become a kind of a memorized phrase, which means biconditional. This symbol is called the biconditional. This is called a conditional, this is called the biconditional. And the biconditional is just the conjunction of the two conditionals in both directions. Okay, good. Now hopefully we can go a little bit faster because what I would now, so that packet is done. There is a new packet, and this new packet, the first is called Propositional Logic Practice. I'm going to give it to you, and you're going to do a bunch of truth tables. Okay, cool. That's page 1. And those will be maybe the last truth tables that you ever have to do in this class, because we're gonna move on from truth tables. Well, that's not true. We're gonna do a lot of truth tables for like a week and then never again. Okay. What do I want to convince you of now? What I need. So what are we doing? The goal right now is to get really, really good at propositional logic. So good that we can produce, that we can do many sorts of propositional logic calculations at just incredibly fast speeds. So what I need you all to do is become in basically 4 or 5 days, savants of propositional logic. And so I want to expose you to many different logical equivalencies. Okay. Some of these you've heard of before. Some of them are famous. So hit the 2 times speed button right now. I think this is better than devoting class time to it. I just think it is. Okay. So true, false, true, false. Okay. So okay. So I know that you all know this already, but still, I persevere. Make not P, make not Q, make not P and not Q, make P or Q, and make not P or Q. Okay, this actually kind of came up on the first packet, I think, but we just sort of skipped through that part. Okay, I can do this all at blinding speeds. So here you just not this, so this becomes false, false, true, true. Okay, great. Here we get false, true, false, true. Here I end these two together, so that gives me false, 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 true. Here I OR these two together, so that's true, except when it's false. And here I take the not of that previous column, which becomes false, 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 true. Okay, ding, 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 ding. I have just noticed something. I have just noticed that this column is the same as this column. And okay, that's just great. What that means is that these two expressions are logically equivalent to each other. And what does it mean to be logically equivalent? It means that they always have the same truth value, regardless of the truth values of P and Q. More sort of precisely, using all the vocab we learned today, what is a truth table again? It's a consideration of every single possible truth assignment. A truth assignment is just an assignment of truth to the atomic propositions. Each row of the truth table is an alternative truth assignment. And when we say that they have the same column, what we really mean is that for every single possible truth assignment, they have the same truth value. Okay, if these are logically equivalent, we have a symbol for this. We say that not P and not Q. Not P and not Q is logically equivalent to not P or Q. Okay. And this one is famous. This is one of the De Morgan laws. De Morgan is a English, I believe, 19th century, yeah, mid 19th century English mathematician and logician who studied kind of sets and was the first person to give names to these kind of basic propositional logic things. And okay, you've heard of this before from ninth grade computer science. Plus, it's just common sense, man. So that okay, here are all the ways to learn the De Morgan laws. One way is to do what we've just done, which is to tediously crank out a proof, so to speak, that they are logically equivalent. Another way to do it is to just use the power of your mind, similar to how we were doing earlier, and to just be like, okay. You know, if it's not the case that P or Q, so if it's not true that P or Q, then it must be that they're both false. Yeah, right? And if P is false and Q is false, then it's not even true that one of them is true. Okay, that's how you, that's one way to do it right there. Okay, so let me say something about this symbol. You will notice that this symbol here, this is the logical equivalent symbol, it's a little bit different. It is superficially similar to the biconditional symbol. P if and only if Q, people just pronounce it that way, but the symbol is called the biconditional. Is an arrow pointing in two directions. Here there's also an arrow pointing in two directions, but it's like with this thing, right? With two instead of one. What's going on there? Okay, well, because this is partially a logic class, and I want you to understand things well, and because I think this does matter, some foreshadowing, maybe this is obvious to you, but we are studying propositional logic. What is propositional logic? It is a formal language. Propositional logic has an alphabet, propositional variables and connectives and parentheses and stuff like that. It has a precise syntax. There are things that you can say in propositional logic, and there are things that you can't say, certain symbols that you can write. It has a semantics, and the semantics of propositional logic is the are truth tables. And it has another thing too, which we'll talk about later. Okay, so that's a formal language, and this biconditional is one of the symbols of the language. The biconditional symbol is a symbol of propositional logic. It is in the language of propositional logic. This string of three symbols, P, biconditional Q, is a string, is a valid and is a syntactically valid string of propositional logic. This symbol, though superficially similar, is philosophically totally different. It is not a symbol of propositional logic. It is a symbol about propositional logic. This statement is a statement of propositional logic. This statement is a metalogical statement. It is a statement about propositional logic. It says that this sentence of propositional logic and this sentence of propositional logic are logically equivalent. In other words, I'm leaving the system to talk about the system. When we say that two sentences are logically equivalent, we're talking about propositional logic. And so this is a metalogical statement. And this is a metalogical symbol. Therefore, I will not give a truth table definition of this symbol, because that would be totally inappropriate and impossible. What is the definition of this symbol? The definition of this symbol is that the truth table columns are the same. Okay, so hopefully that was a good clarification if you needed that. I will now list many other equivalencies of propositional logic. One of them is the De Morgan laws going in the other direction, which it will not prove via truth table because it's just too tedious. So the negation of P and Q is logically equivalent to not P or not Q. Okay, this is quite interesting because, well, it says, let's see, what it says, well, it's not that interesting. It says that if it's not true that P and Q, then one of them must be false. And vice versa, if one of them is false, then it's false that they're both true. Okay, so truth table is sort of superfluous, or at least I'm convinced already with just that. Okay, what else? Some of them are like, I don't know, some of them are so silly as to be almost not worth mentioning, but I'll mention two more. While we're on this subject, note that another slight modification to these two De Morgan laws is to think of it like this. P and Q, therefore, is logically equivalent to not P or not Q. That's a slight modification of this one. And P or Q is logically equivalent to not P and not Q. Okay, and this is something that you've surely encountered before, like in 9th grade computer science, which is to say the and symbol is fully definable in terms of or and not. Back when I used to teach 9th grade magnet geometry, and I taught them a little unit on logic for a couple weeks before we started geometry proper, we would play this game in which we walked around for 24 hours and we refused to use the word and. You never actually need to use the word and. Well, for one reason is you really don't need to use the word and. If you want to say something like, if you're telling someone a story and you're like, I went home, then I had a snack. Or I went home and had a snack. Well, you can just take out the and. You can say, I went home, I had a snack. So, okay, that's kind of a joke. But not even funny, that's just a stupid thing to say. But alternatively, you can delete the word and by replacing it with an awkward sequences of nots and ors. You can say, instead of saying, I went home and had a snack, you can say, it's not the case that I didn't go home or didn't have a snack. And that, if interpreted correctly, means I went home and I had a snack. Okay, that was completely stupid. Where is this going? Well, it means that, it means I don't ever need and. I can do it all with nots and ors. I also don't need or. I can do it with nots and ands. This is if you're doing this thinking about this from a computer science perspective, and you're building logic gates, you don't really need and logic gates. And in fact, a lot of these things are sort of not needed. The reason why I mentioned that, the reason why I mentioned that computer scientists will never use if P then Q is because you don't need these for logic gates, and in fact they're just sort of confusing. Because if I want to decompose if P then Q, well, we've already seen. Did I erase it? We've just seen. I'll just rewrite it here really fast. That the truth table for P arrow Q, we spent a long time in class on this. It's true, false, true, true. In other words, it's false only when P is Q and P is true and Q is false. And so another way of thinking about if P then Q, if you interpret it this way, if you accept this, which we're going to do provisionally for the purposes of propositional logic, this is called the material conditional, but taking this explanation of the conditional, then the only thing required to make this sentence true is, well, if P is true, it's automatically true, and if Q is false, it's automatically true. And so, sorry, did I get that wrong? I did get that wrong. If P is true, it's not automatically true. If P is false, it's automatically true, is what I meant to say. Scratch the last 30 seconds, replace it with this comment. If P is false, that's what we've seen, right? That's if P is false, then if the antecedent is false, then the conditional is automatically true. It's called vacuously true. That was the if Ted Cruz is the Zodiac killer, then every one of those sentences is automatically true for a vacuous reason because the antecedent is false. And so not P is automatically enough to make this conditional true. And if Q is true, which happens in rows 1 and row 3, it's also true. And so, okay, if anything, I'm going too slow, but if I'm going too fast for you, you can simply make the truth table, as I have done here, quite tediously, between this sentence, and you can see that they are, in fact, logically equivalent to each other. What that means is I never need to use the arrow symbol, ever. If I don't want to, I can just express everything in terms of nots and ors. Okay, and then, there's just a million more of these, right? What is P if and only if Q? Well, as we sort of discussed, the interpretation of this is the conditional in both directions. And so, once again, you should just accept this because it's just obviously true, but if you don't believe me, you can confirm this with your own mind by making the truth table. We did this basically already. For P arrow Q, for Q arrow P, anding them together, and you'll see it's the same as the truth table that we stipulated for P if and only if Q. Okay, and so I now introduce you to what's called an adequate set of connectives. An adequate set of connectives is a kind of, once again, this is a metalogical kind of idea. Connectives. It's a metalogical idea that there is a certain set of connectives through which we can express anything we need to. Probably it's true that the biconditional, the conditional, or, and not are sufficient. And that's just true. That I can basically, I mean, those are the only ones I've ever heard of before, so it seems I can probably get away with using just these 5, and in fact, that's true. Another one that's possibly worth mentioning is, well, I erased it, but you may have already noticed that exclusive or can be expressed in a lot of different ways. One way to express exclusive or is to say, well, that's just kind of another way of saying P or Q and not both. That's one way of thinking of P exclusive or Q. Another way of thinking of P exclusive or Q is it's the negation of P if and only if Q. Because P exclusive or Q is basically saying that P and Q have different truth values. But P if and only if Q is basically saying that P and Q have the same truth values. Okay, so I really don't need exclusive or, and I don't really need nor either, right? Because you know, P nor Q is really just logically equivalent to not P or Q. Okay. But curiously, I don't really need or either if I have nor, because it's also true that not P nor Q is logically equivalent to P or Q. I think I've done that right, and that must be true, although that's a little awkward or something. But it's right if someone says, it's not the case that you can have neither soup nor salad, then you must be allowed to have at least one of them. Okay, so it seems that I don't really need nor, but possibly I don't really need or either if I have not and nor. Okay, so and notice that this line can be interpreted as saying that I don't really need the biconditional, and so if I don't really need the biconditional, then this is an adequate set of connectives. You can just kind of trust me on that or something. But since I don't really need the biconditional, this is also an adequate set of connectives. But also note here that I produced a logical equivalence from P if P then Q to not P or Q, which means I don't really need arrow either. I can get by with just or and not. This is just another way of saying you can build a computer with just and, or, and not gates, which is something maybe you already believed. And then, of course, the De Morgan's laws, or at least the 2 versions that I made here and here, are also not just suggest, but show that and is not strictly speaking needed either. So actually just or and not alone is adequate, as is just and not. And you can convince yourself that just arrow and not is also adequate. And there are many, owing to the sort of ubiquity of conditionals in statements of philosophy and mathematics, you might actually want an entire system which is based only on the arrow, which many logicians have done. Okay, and then the shocking thing, but it's probably not shocking to you because I think you covered this in 9th grade computer science, that in fact nor can be you can express not in terms of nor. I'm not going to show you how to do that right now, unless someone asks and no one's here, haha. But in fact, what makes nor so famous is that it is a sort of a binary connective unto itself. All sentences of propositional logic can be expressed in terms of just nors, because you can express not in terms of nor, well, maybe I will just show that. Do I have space? Maybe I'll do it like up here or something. Man. Okay, so P, and then I guess there's only really one possible way that this is going to work, right? Which is to do P nor P. So if you do P nor P, well, what do you get? Well, you have this. Well, okay. The truth table for nor says that it's only true when they're both false. So here they're both false because you're noring this. Some people might find this helpful. You're noring p with itself. So false nor false is true, but true nor true is false. And so in fact, the expression p nor p is logically equivalent with, might as well just throw this in here if we're being completist about this, p nor p is logically equivalent to just not p. Okay, and that kind of completes the proof in a sort of way. That I can express not in terms of nor. Of course, I can express with nor. I can express with nors. I can express nots and ors. And so okay, you see the idea here. All right. I guess the one piece missing from the proof is that I haven't convinced you that this is an adequate set of connectives, but it is. And there's a little activity coming where you're going to basically show that this is the case. Okay. Yeah. What now? Take some kind of screenshot of this or something, or that's not really needed. Maybe I'll take a picture though. Just for my own. This is not the greatest lesson ever, but could be worse. Okay, we gotta make some time, so that's why I'm doing all this. All right, now comes an activity. What I would like you to do is to turn to page 2 and 3 of this packet. It's a 6-page packet called Propositional Logic Practiced. Page 1 was just you cranking out tedious truth tables. Page 2 now also pages 2 and 3 also tedious. This is just an exercise. This is a basically mindless exercise in quickly and efficiently transforming back and forth between different sentences of propositional logic. So in that way, it is not unlike the Boolean algebra practice that you did in 9th grade computer science. And I promise you we're going to do some cooler things soon, but first I need you all to become kind of like savants if you're not already. This is really only like, I don't know, this is like 15 minutes of work. It's more fun if we do it in class, but like, I don't know. Here we are. Here's a sentence. P if and only if Q. I would like to express it using just not and or. Okay, is that possible? Yeah, it's possible. I'm going to show you how to do this. You don't really need me for this, but I'm going to show you what I intend for you to do here. And what I intend for you to do is to use all of the logical equivalencies that we just discovered together, in which you just sort of intuited and absorbed and now are a part of you and sort of memorized in a kind of a way, to convert this sentence, proposition, into a proposition involving only nots and ors. How are we going to do this? Well, I said already that P if and only if Q is just logically equivalent to P arrow Q and Q arrow P. And some people omit the parentheses in situations like that, but I'll just include them. Okay, well, I'm not done yet because I'm not allowed to be using any arrows. Well, it's just the case that P arrow Q can be represented as not P or Q, and Q arrow P can be represented as not Q or P. Finally, we have this and in the center. This is called the main connective of the sentence. And I'm not allowed to use any ands, only ors and nots. Well, now I reach for the De Morgan laws, specifically the version that says that that the negation of, and notice my professional use of parentheses here to sort of chunk what's going on. Cha 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 cha. In other words, this sentence above is roughly speaking of the form x and y. And so you're just supposed to know that something logically equivalent to x and y is not x or not y. That's what we talked about. Okay, and then in here it just goes not p or q. Okay, so I don't know, I've been teaching this for years. This is sort of, for some people it's extremely easy. For other people they just need to put their careful hat on a little bit and have sort of like a good handwriting or something. But anyway, there it is. Okay, how about this one? P arrow Q arrow R. What's up with that? well, now, according to the directions, I'm supposed to express this in terms of just nots and ands. Okay. I guess I know how to do this. Do I? Sure. First off, I'm going to convert these arrows. What's P, R, or Q? It's not P or Q. But then also, thing, arrow, R is just like not thing or R. So now, in sort of one step, I got rid of the arrows and replaced them all with ors. Oh, damn. But now I want nots. Or rather, I want it to be in terms of just not and. So I actually need to get rid of both of these ors. How am I going to do that? Well, for one of them, I can just distribute. Well, let's see. Do I want to do that? Distribute this back through. So P and not Q. There's a couple different ways of doing this, I guess. So that got rid of one of the ors. This is me just applying the De Morgan laws. But now I need to get rid of this or, this main connective or. Well, that's just the same thing as not P and not Q and not R. Okay, I mean, this is really a lot like the Boolean logic stuff that you did, but this is, in some ways, this is like less efficient. But okay, pushing on, P and Q arrow R. Well, how should I do? Oh, I'm supposed to do just nots and ors. Okay, that doesn't seem too hard. Let's see. Maybe I just do this on one step, show off style, because this X and Y format I now know to be really convertible into not X or not Y, and in this case Y itself is not Q or R. Okay, so once again, becoming savant in propositional logic. I don't know, I guess I just keep going or something. For P or Q, I want to use that using just not an arrow. I mentioned that was possible. I didn't prove it, so here's the proof, I guess. That or is unnecessary. What's that word? Yeah. If I have not an arrow, I don't need or. What should I do? Well, yeah. I mean, right? This is just not P arrow Q. Here's how my brain processes this. Well, I just have sort of memorized that X arrow. Well, I don't even know how to process this. This is just true, right? Because the interpretation of arrow is like not the antecedent or Q, and so there it is. Maybe, I guess, if that's not sort of obvious to you how I did that, then you could maybe think of this P as like not P, which is another maybe logical equivalence that's worth mentioning. In propositional logic, not P is logically equivalent to P. It's actually mildly controversial, but in classic propositional logic, that's certainly the case. If you just make the truth table, you will see. Why is that helpful to rewrite it like this? Because now this is kind of like of the form, like not something or Q, so maybe that's now sort of just more obvious or something that's the answer. Okay, and then can I express and in terms of just not and the arrow? Yeah, I guess I can. Personally, I just kind of do this in a bit of a roundabout fashion. So P and Q to me is not P or not Q. And then, well, that is just going to be not P arrow not Q. Okay, I'm gonna maybe stop this. In a normal class, I would probably, if this was a normal year, I would do just like one problem maybe, like just number one alone, and then I would just kind of let people go, just like do their own thing. And some people would just blitz through this in 5 minutes, other people would kind of be more slow and careful, and then anyway, you're just gonna finish the rest for homework. So maybe I'll just do like one more together, or maybe I don't need to do that. Maybe I just trust you. So you do these. You're going to finish the rest of page 2 and page 3 for homework. Pretty fun. And if you're struggling with this a little bit, or you just find it to be kind of hard, or you want some more direct advice, we can do a problem or two at the beginning of class on Tuesday, or this is the kind of little thing that you can maybe get help with on during the Wednesday check-in or some other time. I don't know how that's going to work. Okay, go to page 4. On page 4, you will see a cute big chart here. Here's what it says. The following truth table is a table of the 16 possible binary connectives. All right, that's already kind of fascinating because note that, okay. When I used to teach math and geometry, I would have a whole conversation with my class. I would say, hey, how many connectives are there? Because I taught them, you know, arrow and biconditional and or, and it seems like every day I just kind of introduced like a new one, and there's seemingly many more around the corner, and then they sort of dry up and we suddenly stop talking about them. So a very reasonable question is, how many binary connectives are there? And you know, it's a great conversation to have with 9th graders, and a lot of them are like, infinite number of them or something like that. Okay, so we need to sort of clarify our terms. There's nothing stopping you from, you know, defining some exciting new connective, and maybe, you know, maybe you want it to be like a monster, you know, like a scary monster connective. All right, but when it comes right down to it, if you're going to give the definition of P monster Q, and your definition is like true, false, true, say, well, dude, that's not a new connective. That's just arrow. You just defined a new picture to refer to arrow. So I'm not talking about how many different names there could be, or symbols there could be. I'm talking about how many fundamentally different binary connectives there could be. And since the connectives are all, within propositional logic, truth functional, then any connective can be fully defined by the particular 4 entries associated with the 4 possible truth assignments, assuming this is a binary connective. So it can only depend on the truth value of P and the truth value of Q. There are only 4 options, so there are only 4 possibilities. In other words, this is just a long-winded way of saying that the definition of a binary connective is uniquely determined by its truth table column. And so the question of how many binary connectives there are reduces to the question of, well, how many possible columns, different distinct columns can there be? And the answer is that, you know, it can be here either true or false. So this is, you know, 2 to the 4th, so it's 16. Okay, so there are only 16 possible connectives out there, and what you have before you on the paper is all 16 of them. And your job, this is again just playing around with propositional logic until you get really good at it, is to to sort of label the header of the column with some truth, with some expressions of propositional logic formulas. But to make it kind of challenging, you are only allowed to use 2 propositional variables. So that's the P's and the Q's. So you can't say like P and Q, or P or Q and not P and Q, something like that. So you need to be a little bit more concise than that. And it is possible, by using all the connectives you've heard of, it's possible to do this. And okay, once you've done this, then you're close to a proof that in fact there are no sort of mysterious other connectives out there that you haven't heard of that are crucial. Okay. Oh, note that bottom comes up somewhere in this. Bottom is also a connective. It's not one that's super famous, and you may not have heard of it. And okay, do we really need it? Maybe not. But it is a very cute connective. It is a just like and is a binary connective, and not is a unary connective. It connects one proposition together to make a new complex proposition. Bottom is a zero-ary propositional connective. It is a connective which just connects no propositions together. And the truth table for bottom is very exciting. It's just false. And I'm not even sure how I'm supposed to write this again. I guess like it's like this. Yeah. I guess maybe even you do something like No, I guess you just don't even do anything here. I think this is what I'm supposed to write. Yeah, there we go. So it has it connects 0 connectives together. So therefore, there are going to be 2 to the 0 equals 1 rows in the defining truth table for that connective, and it's just false. Okay, it's a symbol which is merely always false, and so but it's a legit symbol of propositional logic. For example, you can write bottom arrow Q. And that is the legit proposition of propositional logic, and in fact, it's always false, right? Okay, and something like something like P arrow bottom, that would be a tautology. In fact, because no, I got that backwards. Well, whatever. I might have said the wrong thing a minute ago. Sorry, I don't know I've already forgotten what I said. But I think what I meant to write was this. That is a tautology. That is always true, regardless of whether P is true or false. Because false arrow anything is true, and bottom is always false. Okay. Good. More basic things of propositional logic. We're just going to finish this packet. Or you're going to finish for homework, I mean. Some other things that every 8th grader should know. Okay, so you have these famous kind of conditionals. P arrow Q. This is called a conditional. Conditional. Okay, woo! Well, because conditionals are so sort of ubiquitous, this is probably one of the most useful things to teach to someone who's just starting to learn geometry, is this thing called the converse. Q arrow P. You may have noticed, if you were very observant or reading the chat or both, that I made a mistake at the very beginning of class, and I was introducing this packet, and I said all rectangles are squares. That sentence was printed on my packet as an example of a proposition. It is a false proposition, but it is still a proposition. And I, forgetting that I was being so cute as to put a false proposition in there just to keep you on your toes, missed it and alluded to it as being true. It's not true. I made what's called a converse error. This is the converse. The converse of a conditional is the conditional with the antecedent and the consequent reversed. And the thing to know about the converse is that it is not logically equivalent to the original conditional. This is P arrow Q, but this is Q arrow P. Okay, you've seen this already, so this is a little bit silly, but this is true, false, true, true, but this just isn't, man. This is true, true, false, true. And so a proposition is not logically equivalent to its converse. They are different, and that's a confusion that people can make every now and then. Okay, so don't be that person. There's also this thing called the inverse. This is less commonly really needed, or no one really cares about it. So what is the inverse? It's the not P arrow not Q. This is all in reference to a particular conditional. Q arrow P is the converse of P arrow Q. Not P arrow not Q is the inverse of P arrow Q. And okay, if you go to, I guess we're just going to do this. Not P, not Q, not P arrow, not Q, la 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 la. And what do we got here? False, false, true, true. This is false, true, false, true. And then I'm taking the arrow of these two. Well, false arrow, false we've seen already is, well, this is just, what the hell's going on here? Yeah, true, true. And then this is the only one that's false. Oh, what have I just discovered? I've just discovered this. That, in fact, the inverse is logically equivalent to the converse. And finally, I think you all maybe know these terms. I would think that you would, but who knows? Not P arrow not Q is called the contrapositive. Contrapositive. Once again, it's the this is the contrapositive of the. These are all sort of in reference or something to the original. This is the converse of that. This is the inverse of that. This is the contrapositive of that. And the contrapositive. Well, I have enough space to just sort of do it right here is yeah, false arrow false is true, true arrow false is false, false arrow true is true, and true arrow true is true. So what do I just learn? I learned that, if I didn't somehow know this before, that the contrapositive is logically equivalent to the original conditional. Okay, so this is good little pieces of vocab to know if you're doing math or logic. And then you have this little activity on page 4, which is I've given you a sentence designed perhaps to be kind of quite tricky, and I want you to do the following. First, tell me whether the sentence is true or false. Then, write out, in mathematical language, the converse. Then, tell me whether the converse is true or false. If the converse is true, great. If the converse is false, please give a counterexample showing that it is false. And do the same for the inverse and the contrapositive. It's actually a little bit tricky. I think these used to be problems on the logic test, so you have to sort of be a little careful there. Okay, the final thing, turn to page 5. We're just finishing this packet. Yeah! This is a really boring video. I hope you're like, watching on 1.5 speed and just like, I don't know what you should be doing to be happy. You should just eat some chocolate or something. Okay, what is the whole point of studying propositional logic? Well, I alluded to the fact that the answer is different depending on what kind of person you are. But for the people who originally developed propositional logic, like, Aristotle is the first person to care about this enough to write about it at length, that we have records of, and he was trying to analyze philosophical argumentation. The whole point of logic, you might say, one of the perspectives, is that we are engaged in vigorous debate, whether that be legal debate, political debate, philosophical debate, or perhaps mathematical debate. And oftentimes we find that though there is intuitively some shared mutual understanding of the basic logic principles, people speak in error. They make, for example, converse errors. And so logic is a way, a neutral way, you might say, to kind of to codify the underlying logic that we use in everyday argumentation. Okay, great. The mathematicians, I will note, they found logic sort of less necessary. The people who were doing math, they more or less got their logic right. They didn't really need this propositional logic structure to help them, but okay. Where am I going with this? Where I'm going with this is one of the whole reasons to care about propositional logic is to analyze argumentation. So what is an argument? Well, an argument consists of a set of premises and a conclusion. So it's like, premise 1, premise 2, who knows how many premises there are, and then there's some kind of conclusion. Okay, what makes an argument a good argument? Well, a good argument is an argument that you can follow and it will lead you to the correct places, or something like that. A good argument is one you can trust. In particular, if this premise 1 is true, and if this premise 2 is true, then we would like our conclusion to be true also. And that's just what a valid argument is. There are many different ways of explaining argument validity. So this is now a sort of a new concept, right? A proposition is either true or false. But an argument, which has a set of premises and a conclusion, is not true or false. The argument is either valid or invalid. And the validity of the argument depends on both the premises and the conclusion and their sort of relationship with each other in a kind of a way. Okay, so what have I written on my paper? An argument is valid if and only if all truth assignments that satisfy the premises also satisfy the conclusion. So whenever the premises are true, the conclusion must be true in order for an argument to be valid. Notice that an example of let's just jump in. Okay, so this is I think we just do a couple examples. So here's an example. P arrow Q, P therefore Q. Okay, this is maybe the most famous kind of logical argument. It's very sort of simple, boring, obvious, you might say. It has a name. It is called, well, everyone calls it modus ponens. These are old Latin names, and that's because the ancient Greek society was extremely influential in the Roman society, and especially within the church. So the works of Aristotle were sort of translated and retranslated into Arabic, into Latin, and studied forever. But the names that the Europeans used to refer to these arguments were Latin names. And this, okay, I don't speak Latin, I don't even know anything, but I think this is actually short for something even more ridiculous, like modus ponendo ponens. And that means, well, you can look it up, but it's something like that thing which was the thing, or something, some kind of crazy gerund or something like that. I forget. If we were doing this live, someone would just look it up and tell me, but it's not important. The names are not important, I believe, at all. But what is important is this argument is valid. Why is this argument valid? This argument sort of structure, or any argument of this format is valid. And the answer is that when this is true and this is true, then this must be true also. Okay, how do we know this? This is what, truth tables sort of to the rescue. Well, here we go. This is a pretty short argument. I'm making a claim, when I say it's a metalogical claim, about the relationship between the truths of the premises and the conclusion. So let's just do it. Let me just quickly make this truth table. True, false, true, false. And then, okay, this we just know to be true, false, true, true. Okay, great. Well, now here's what we're going to do. We need to know: can I trust this sort of conclusion when these premises are true? And so all we care about are the truth assignments in which these premises are true. And so now what we do is we go to the truth table, we look for the rows of the truth table in which the premises are true. Well, P arrow Q is true, almost always. When is P true? Here and here. Therefore, I claim that there's only one row of this truth table in which these premises are both true. Only when, there it is, right? Only when P is true and Q is true, only in the truth assignment associated with row 1 of this truth table are these premises both true. But in that case, when the premises are both true, the conclusion is also true. Therefore, I can trust this argument sort of forever now, right? Whenever these two are true, this will also be true. And this is what's called a valid argument. Okay. And I'll notice that the validity of the argument sort of transcends the truth of the propositions. If you had some kind of, here we go, ready? I will say something like, if, maybe this premise is, if you heat, tin, you get gold or something like that, and P is like, that you heat tin, and Q is that you're going to get gold. Maybe if you heat tin greater than 500 degrees, so that's like really hot or something. Okay, so here we have two premises. If you heat tin, I don't even know what the hell I'm talking about at all, but tin is not one of the I guess lead. I don't really remember what the hell they thought they were going to make gold out of. But if you heat tin greater than 500 degrees, then you will get gold. That's just false, okay? It turns out to be just false. But that doesn't change the validity of the argument. This is false, and here, maybe this is true, and I can get a false conclusion. So you can get a false conclusion by following a valid argument. It's not like it's some kind of omniscient, all-powerful technique. It depends on the propositions being true, but if you feed it something true, then you will get something true back. Okay, I hope I made that point clear. Alright, let's do another one. Let's do this one on the bottom of the page. So by the way, here we have this packet. I'm about to wrap up this video, but pages 5 and 6 of this packet are just blank, except for some obscure words, some in English, some in Latin, many of which you've never heard before. So via the power of Googling or who knows what, you're supposed to figure out what all these arguments are. You know, go to Wikipedia, they have a list of them all. And what I want you to do is, please really do this and take it seriously, this is a real class, go through and determine and, justify to me implicitly that these arguments are valid if they are valid, and that they're invalid if they're invalid. And how do you do that? There's only really one way at this point, and that's to make a truth table. Okay, so we're going to master this technique so that we can leave it behind, but first we're going to master it. So there's this thing called denying the antecedent. Denying the antecedent. It goes like this. I'll just tell you, if you look this up, this is what you would find. If you Googled this phrase, you would find that this is the argument. P arrow Q, not P, therefore not Q. Alright, if you don't think about that at all, it sounds like at all, maybe it sounds kind of good, right? Well, if P then Q, but not P, so therefore not Q. Alright, but, let's do it. So here's PQ, here's not P, here's P arrow Q, and here's not Q. Let's go. Last truth table of this video, and then you have so many more to go. So true, true, false, false, true, false, true, false. Okay, and then not P is false, false, true, true. This is true, false, true, true, and this one is false, true, true. Oh my god, this is so long. Okay, well, now, what does it mean to check to see if this argument is valid? I examine the premises and the conclusion. What are the premises? P arrow Q and not P. Okay, well, when is P arrow Q true? It's true in rows 1, 3, and 4. When is not P true? In rows 3 and 4. Therefore, there are 2 rows of this truth table in which these premises are both true. And so I will now circle for reference the row 3 and row 4. Those two, there are 2 sort of truth assignments in which the premises are true. And is it true in both of those, in all of those truth assignments, that this conclusion is true? Aha! No, it's not. There's this offender right here. And this offender is in fact false. In other words, we now say, unlike over here, where we concluded, I forgot to write it on the board, where I concluded that this argument was valid, here, this argument is invalid. And it's invalid because under some circumstances, specifically the circumstance in which P is false and Q is true, the premises are both true, but the conclusion is false. Therefore, this argument is not to be trusted, because sometimes this argument will lead you astray. You can, following an argument like this, begin with false assumptions. Begin with true premises, and yet arrive at a false conclusion. So that makes this argument bad. We should never use this argument. And the reason why it has a name is because, people make mistakes, especially philosophers. They're very concerned with their agendas. And, you could have some famous philosopher, writing a whole thing, and perhaps it's the case that they're just making an elementary logical error. That's the kind of thing that people do. And so if you want to be like a real pedant about this, then you memorize the names of all of the possible famously sort of famous invalid arguments that people sometimes make, and you mid debate you just stop your opponent. You say, aha,
You are performing the error of denying the antecedent. And in a sufficiently sophisticated, educated audience, everyone will know, denying the antecedent, of course. Well-known, logical invalidity. And anyway, that's someone who's reasoning according to this form. You will find examples of this out there, Okay, good! Your job is to watch this whole video. It's so long, I really hope you watch the whole thing on 2 times speed. Then you are going to do this entire 6-page packet. I guess just do it by Tuesday, man. Let's just kind of push on. Next week we're gonna do something more fun. Good job, goodbye.